Everyone, my name is Tariq Majid and I'm being supervised by Dr. Hamza Safir. So the topic of my short presentation today is introduction and synthesis of 2D materials. Specifically, we'll talk about the molybdenum disulfide MOS2. So the outline of my presentation is starting with the history and origin, then comes up introduction, then we have some applications of the 2D materials, then motivation, and also we have different method of synthesis. Especially we will talk about CVD method, which is the most suitable method of this, and then we will conclude the results. So the history of 2D material starting like in 1859, Body made a failed attempt to exfoliate a single sheet from graphite. This was the failed attempt, but this gave rise to and give an idea to many scientists to work on this in this field. And after that, R.E. Pearls and L.D. Landau in 1937 suggested that strictly 2D materials could not exist because they tried many times, but they were not able to reach the desired results.
एक क्वेश्चन है इनका क्वेश्चन कि 2D मटेरियल को 2D मटेरियल क्यों कहते हैं 3D तो हमें पता दुनिया 3D है 2D क्यों कहते हैं
डायमेंशंस की वजह से कहते हैं ना। जैसे आप देखें क्यूब को देखते हैं वो 3D में होता है, लेकिन 2D में 2 डायमेंशन ही है, उसकी थर्ड डायमेंशन ही नहीं है।
नहीं यानी उसकी हाइट वो है
हाँ, मतलब आप देखेंगे ना, एक शीट को देखें या मेरे पास कोई ऐसी सिस्टम जगह चीज़ नहीं है, एक पेज को देख लेना आप, हाँ ये पेज है जैसे, तो लाइक इसकी कोई हाइट नहीं है, बिल्कुल ऑलमोस्ट जीरो है, अप्रोचेस टू जीरो,
एटॉमिक लेवल
एटॉमिक लेवल,
हम हाइट इसकी कम
हाइट कम है
इसलिए
बिल्कुल, ऑलमोस्ट जीरो।
ये फर्दर जो है ना हम इसको मजीद नहीं कर सकते
जी,
एटॉमिकली ठीक है
एटॉमिकली
इससे ठीक तो नहीं हो सकता एटॉमिक एटम से तो नहीं हो सकता
जी सही। And after that, graphene was first introduced, like it was given the name graphene in 1862 by Hans Peter Bohm. And after that, the practically work in the introduction of 2D materials basically start in 2004 when two scientists in, I think, UK, uh, the name was Jaim and Nozzle, got works. They were successfully exfoliate the single sheet of graphite in 2004. What was the method actually? How they exfoliate the single sheet? I will just explain in next slides. And after that, on their work, they got Nobel Prize in 2010. However, the history of 2D materials extends beyond graphene. The first 2D materials we known about, like in 1862, Phil Simons and Robert Young demonstrated the existence of single layer, but it's not practically, but just an existence. A member of the 2D material, TMD family, which has since become now the prominent member of the 2D materials. How graphene was discovered? It's a very interesting phenomenon actually. The scientists like took the bulk form of the graphite and they stuck the scotch tape on it, and then doing this synthesis again and again, they were able to reach the single layer of graphite, which is now we are like saying graphene is the most stable structure. It's the honeycomb structure. This method is also known as the mechanical exfoliation. Now let's introduce 2D materials. 2D materials are substances with a single layer of atoms or molecules. They possess unique properties, like they have very less dimensions and they have exceptional electrical and thermal conductivities, optical characteristics. As I told you, the graphene was the first ever discovered 2D materials. It's a single layer of carbon atoms. Also, we have another 2D materials belongs to the TMD family, molybdenum disulfide and the tungsten disulfide, MOS2 and WS2.
what is this TMD
TMD, sorry, transition metal dichalcogenides. So,
transition metal डाई का मतलब क्या होता है
two. I will explain in next two slides. Yeah. Now, what are TMDs actually? Yes. So in TMDs, we have a transition metal and we have a chalcogen atom. What the formula is MX2 means that one transition metal is just sandwiched between the two chalcogen atoms. So MX2. So why we are using TMDs? Because they are semiconductors and they can give the good results when they are converting into 2D materials. They can give us a very high electrical conductivity and also the optical characteristics as well.
तो 4 से तरफ क्या करना है ट्रांजिशन होते हैं लेकिन हमारे यूज को जैसे सारे ट्रांजिशन मैटर हमारे काम के लिए जो कि टीएमडी बनाते हैं
सर ये जो है ये हम बाकी भी नहीं यूज़ कर रहे, सिर्फ सल्फर, सेलेनियम और ये यूज़ कर रहे हैं।
बाकी बनाते नहीं है ना, फॉर एग्जांपल ऑक्सीजन भी बनाता है, ठीक है, वो डिफरेंट मतलब यही तीन जो है ना, सल्फर सेलेनियम नॉर्मली यही बनाते हैं।
Okay. So now let's talk about the main material, which is molybdenum disulfide. It's a very interesting material. It has wide range of applications as semiconductors can be used in electronics for the transistor and optoelectronic devices. Its unique properties also make it useful in catalysis, and also it can be used in solar cells, supercapacitors, and batteries as well. So, and the structure of the molybdenum disulfide is like one transition metal sandwich between the two layers of the chalcogen atoms. And why it's very important? Because its storage structure provides high surface area. It's very important, like high surface area and mechanical flexibility, making it versatile for use in the technological advancements. And now we have applications.
एक जो सबसे इम्पोर्टेंट क्वालिटी है ना एमओएस ये रेड बैंड गैस है।
जी सर।
तो किया आपने?
सर उसको एक्सप्लेन नहीं किया, मैं कहा कि एक्चुअली होता क्या है कि हमारे पास जो बल्क फॉर्म में मटेरियल होता है वो इनडायरेक्ट बैंड गैप होता है। जब हम उसको स्टडी करते हैं हम देखते हैं उसका इनडायरेक्ट बैंड गैप होता है, और जब हम उसको सिंगल लेयर पे कन्वर्ट कर लेते हैं तो वो इन डायरेक्ट बैंड गैप हो जाता है, जिसकी वजह से ये उसकी प्रॉपर्टी होती है कि वो उसकी इलेक्ट्रिकल कंडक्टिविटी बहुत ज़्यादा हो जाती है। ये मेन मतलब रीज़न था कि उसकी इलेक्ट्रिकल कंडक्टिविटी इतनी ज़्यादा क्यों होती है। So we have different applications of MOS2. We can like have used in energy storage and conversion, also in electronic devices, electrocatalysis, photocatalysis, sensors, and biomedicines. Should I explain one of them? Electronic devices mainly we can replace typical transistors with 2D materials because they have exceptional electrical conductivity. So that will be good if we can use 2D materials in the electronics. And also, what is the use in energy storage conversion and like in solar cells, supercapacitors, batteries? Why we are using 2D materials in this field? The reason is the high surface area. If we have high surface area, then more number of ions can be deposited on the surface, and we can store large amount of energy. Also in medicine, electrocatalysis. In electrocatalysis, we can use 2D material to increase the reaction rate. All right. Okay, so what's the motivation behind to work on the 2D materials is that like they have exceptional properties, as I told you earlier. It's electrical conductivity, thermal conductivity, and optical characteristics. So I believe that in future world, if we work on this field, then um, we can work like we can explore more properties of 2D materials as well. Now comes up on the synthesis method. We have different synthesis method to study. Like the first one is chemical vapor deposition, which is the main method, which is explained in next slides. So I will not talk here. The second one is mechanical exfoliation, which is the same like the Scotch tape method. Third one is liquid phase exfoliation, hydrothermal synthesis, and then sol gel method. Now comes up on the main idea, which is synthesis of MOS2 by CVD. It's very interesting. सर वो अभी मेरे से नहीं हो रही थी, मेरे बाद में So this is this we have a chamber actually. In this chamber we have first of all the first step is the preparation of substrate. The substrate here is made of the silicon wafer, and also we have here is the material. Now we are talking about the molybdenum disulfide. So in this chamber we have material MOS2 and we have silicon wafer where our monolayers will deposit, and also अच्छा अलग अलग है वो, अच्छा अच्छा, फिर वो रिएक्शन बाद में करेंगी।
वो रिएक्शन बाद में करेंगे, सल्फर अलग से क्रिएट होगा, गैस बनेगा, और मोलिब्डेनम ऑक्साइड में ऑक्सीजन तो खत्म हो जाएगा, मोलिब्डेनम मेटल मेटल रह जाएगा, उसके साथ फिर सल्फर रिएक्ट।
So after that, the one more most important thing, in this chamber we have at least 600 to 1000 degrees C temperature, so that we can 850 to 1000. Only 850. Only 850. All right. So after this,
लेयर्स को चेंज करने के लिए 5 लेयर चाहिए, आप 4 लेयर चाहिए,
अच्छा,
लेयर्स के लिए।
so after that, actually this cylinder is known as the argon cylinder. We can introduce the gases. we will introduce the argon gas, which will react with this material, and then there will we will heat from this side, like from the silicon wafer. And when the temperature of the chamber will be about 1000 or 850 degrees C, then there will be a reaction between the argon gas and then this material, and then
आर्गन गैस इनर्ट होती है, तो ये मैं बताता हूँ केमिकल वेपर डेपोजिशन का मतलब है कि हमने केमिकल वेपर को कहीं पे डिपॉजिट करा, इसका मतलब होता है केमिकल वेपर। ये क्यों करने से इसके अंदर वो सिलिकॉन पड़ा हुआ है और ये सल्फर पड़ा हुआ है और मोलिब्डेनियम ऑक्साइड, दो पाउडर्स पड़े हैं अलग अलग, ठीक है। मोलिब्डेनियम ऑक्साइड पाउडर को हम हीट करेंगे 850 डिग्री सेंटीग्रेड पर ऑपरेट हो जाएगा, सल्फर को हम ऑपरेट करेंगे 300 डिग्री सेंटीग्रेड, दोनों अलग अलग पड़े हैं और वो सिलिकॉन वेफर इनके ऊपर पड़ा हुआ है, ऐसे ऊपर, इधर देखो ये ऊपर पड़ा हुआ है, ये नीचे पड़ा हुआ है, ये दोनों वाइब्रेट कर रहे हैं। आर्गॉन गैस हैवी होती है, ठीक है, और इनर्ट होती है, रिएक्ट नहीं करेगी। वो सिर्फ काम इतना करेगी जो सल्फर वाइब्रेट हुआ है उसको पकड़ेगी, यानी उसको अपने साथ उठाएगी, वो मोलिब्डेनियम ऑक्साइड तक ले जाएगी, वहां पे वो दोनों वेपर फॉर्म में रिएक्ट करेंगे और डिपॉजिट हो जाएंगे सिलिकॉन वेफर के ऊपर और हमारे पास लेयर्स ग्रो होना शुरू हो जाएंगे, ठीक है, ऐसा।
all right, so this was the chemical reaction, and in this way we can have the deposition of the monolayer successfully on the silicon wafers. And after that, the next step is is the same like growth of layers and substrates. So we can cool down after deposition. We can cool down the temperature of the chamber, and then we can remove the monolayers from this. And after that, we can do characterization like XRD, Raman spectroscopy, or FTIR. So here I can conclude my results. MOS2 is an exciting 2D materials with exceptional properties. Since this method has diverse and offers stability with its unique characteristics, MOS2 holds premises for the large range of applications. Further research in MOS2 is likely to lead to exciting advancements in various fields.